Okay, so this is Math 2250. This is an electronic virtual lecture in lieu of the fact that we could not meet on Friday, December 3rd. Today, we're going to cover 6.3 as well as 6.4. 6.3 is orthogonal projections onto a subspace. So here's the problem we're going to deal with. Suppose you're given a subspace, so W in Rn is a subspace. And suppose you're given a vector Y in Rn. Okay, and so what I want to compute is this vector in W, which is the projection, the orthogonal projection of Y on W. So the orthogonal projection of Y on W. What does that mean? That's this vector here in W, let's call it little w. W has two properties. W lies in W, and so that's W, and then W is orthogonal to this vector here, which is Y minus W. So W is orthogonal to Y minus W. So those are the two properties. And I'm going to show you a formula for W. So theorem. So the projection of Y onto the subspace W is given by the following expression. You take Y dot U1 over the length of U1 squared. Oops, we need something before we do this. I have to back up, sorry. So let's assume we are given, that we're given a bunch of vectors U1 through UP, which is not only a basis, but an orthogonal basis. For W. And in 6.4, I'm going to explain how to build an orthogonal basis. So suppose you're given one. So then the theorem says that W, which is the projection of the vector Y onto the subspace W, is given by Y dot U1 over the length of U1 squared times U1 plus Y dot U2. You've seen these weights before. These weights occurred when we found the projection of the vector Y onto a line, etc. Y dot UP over the length of UP squared times UP. So that is the claim, that is the formula that I wanted to state for the orthogonal projection. So let me explain how this is proved. So the proof goes something like this. So what you have to show is that, well, clearly this vector, the sum of these terms in the right side of the box, is a vector in W because it's a linear combination of the vectors UI, and each UI is sitting in a basis for W. So this property is okay. It's a second property we have to verify. So we have to check that Y minus W dot product with W equals 0. That's all we have to do. Oops, that's not a vector, that's a scalar. And that's the same thing as checking that Y dot w dot w minus w dot w equals 0 by the distributive law, and that's the same thing as checking that y dot w equals w dot w. Well, you can compute y dot w using the expression in the box if this vector on the right is called w. And what do you get? Y dot w is the dot product of this expression in the box with w. And what is that? That's going to give me that's going to give me y dot u1 over the length of u1 squared times y dot u1. I'm using the distributive law. I'm taking this stuff on the right side in the box, and I'm taking on a dot product on the left with y. So you're going to get y dot u1. And then so on, all the way to the end, we get y dot up over the length of up squared times y dot up. So that's y dot w. What about w dot w? Well, we could also, so w dot w is this expression on the right in the box dot producted with itself. Now, every time you have a ui dot producted with the uj, that's going to be 0 unless I equals j. So the only terms which appear to be non-zero are those which are given by taking y dot u1 over u1 squared, u1 dot producted with itself. So this gives me, it's going to give you at the end, the first term will be this dot producted with y dot u1 over u1, over u1 squared u1. So that's like the first term, and then there's more stuff. And if you think about what this thing, this is, it's going to be the same thing as this. So this and this are the same. And likewise, all the remaining terms are the same. So that sort of gives you a sketch of the argument why this is true. Okay, so let's, I think what we should do is do an example. Okay, so here's an example. Suppose y is 6, 3, minus 2. So that's a vector in R3. And suppose w is the span of the pair of the orthogonal basis 1, 1, 0. I'm sorry about the dogs. 1, minus 1, 0. So these are orthogonal vectors. So this is u1 and this is u2. So what I want to compute is the projection of y onto the subspace W. So what do I got to do? I got to compute, in this case, I got to compute the y dot u1 over the length of u1 squared times u1 plus y dot u2. There are only two vectors, over length of u2 squared times u2. So let's compute the various things. So what's y dot u1? Well, that's 6, 3, 2 minus 2 dot product with 1, 1, 0. And that's 6 plus 3 is 9. Then there's y dot u2 we're going to need to compute. That's going to be 6, 3 minus 2 with 1 minus 1, 0. So that's going to be 6 minus 3, or 3. Then we have to compute the length of u1 squared. That's going to be 1 squared plus 1 squared plus 0 squared, which is 2. Then we have the length of u2 squared, which is 1 squared plus minus 1 squared plus 0 squared, which is 2. And now we're ready to write down the projection of y on w. So it's going to be 9 over 2 times u1, which is 110, plus 3 over 2, 3 over 2 times 1 minus 1, 0. And what do you get? Well, you can do the arithmetic and you'll see that you get 9 plus 3 is 12. 12 halves is 6. I should write a 6 here. Sorry, 9 halves plus 3 halves is 12 halves or 6. Then we have 9 halves minus 3 halves, which is 6 halves, which is 3. And then we get 0. So that is the projection of y on the subspace W. And that's the answer. Okay. So let me now list the properties of orthogonal projection. Onto a subspace. So here are the obvious properties. So if y lies in W is a vector, then the projection of y onto W. So if you started off with a vector in W and you project it, that should be no arrow there, and you project it onto W, that's going to be y itself. That's if you start off with something in W, nothing new. Okay, so then the second property is if you remember the picture that I had of the orthogonal projection, here's y, and here's its projection. Then this vector here is calculates the distance from the head of y to the plane. So if W is the projection of y onto the subspace W, then the distance from y to W is given by the length of the vector y minus W. Okay, and then the third property I'd like to mention is that if U1 is not through UP is not just orthogonal, but orthonormal, basis for W, then the projection, the formula simplifies slightly. It's given by y dot U1. Well, the length of U1 is 1, so there's no denominator with that weight, etc. Y dot UP times UP. So the formula becomes very simple. And you can think of it in the following way. So if we set U equal to the matrix whose columns are the vectors U1, U2, etc., then this is the same thing as writing U transpose times U times Y. So in other words, you take this matrix and take U transpose, multiply U transpose times Y, you get the projection. So that's kind of a cool formula. Okay, so that is 6.3. There's nothing more to do in 6.3. We now turn to 6.4. So 6.4 is called the Gram-Schmidt orthogonalization process. So here is the problem. The problem is find an orthogonal basis, or an orthonormal basis if you want, by dividing by the length of the vectors for a subspace W in Rn. So here's the method. Okay, so here's the method. Okay, and it goes like this. Let's go back to black. Okay, so let's let x1 through xp be any basis for W. And now I'm going to modify it to get a new basis, which is orthogonal. So here's the algorithm. So step one, let's define a new basis. Let's set W1 equal to x1. Okay, so there's nothing new. W1 is the first vector. Okay, step two, we're going to take W2 and define it in the following way. We're going to do the following. So suppose here's W, right? And we have the first vector already chosen. So that's x1, which is W1. And now suppose we take the next vector and it's called x2. Oops. Now what I can do is I'm going to replace x2 by something else. I'm going to replace it by the dotted vector here, which makes a perpendicular and orthogonal, is orthogonal to W1. So what I have to do is I have to take the projection x2 and subtract off the projection of x2 onto the line spanned by W1. And explicitly what that is that this is given by x2 minus x2 dot W1, which is x1, of course, over W1 squared times W1. So that's what W2 is. So W2 is that. So let's go to the next one, W3. So W3 is x3 minus the projection of x3 onto the span of W1 with W2, which is the same as the span of x1 with x2. So what that is x3 minus x3 dot W1 over the length of W1 squared times W1 minus x3 dot W2 over the length of W2 squared times W2. Okay, you can keep iterating this procedure. So the last step is to get the vector WP, and that's going to be XP, the pth basis vector in the original basis. We subtract off the projection of XP onto the span of the vectors W1 through WP minus 1. So what does that give me? That gives me XP minus XP dot W1 over the length of W1 squared times W1 minus XP dot W2 over the length of W2 squared times W2 minus dot, 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 minus. And the last step is XP dot WP minus 1 over the length of WP minus 1 squared times WP minus 1. Okay, so that's the formula. I'm going to do an example to show you how to compute with this. So, but let me remark that this produces an orthogonal basis. This produces an orthogonal. So by the way, I wrote step 1 here. This would be step 2, and this would be step P. After step P, you're done. So this produces an orthogonal basis for W. Okay. So if we want to produce an orthonormal basis, we would take these vectors and rescale them so they're unit vectors. And I won't write down the formula for that. So let me just do a single example. Here's an example to show you. It's not hard. Suppose W is the span of two vectors in R3, which is given by 1, 1, 1, and 1, 1, minus 1. And I want to find an orthogonal basis for W. Okay, and then maybe even an orthonormal basis. So what we're going to do is we're going to set W1. So this is 1, 1, 1 is X1, and X2 is 1, 1, minus 1. So W1 equals X1, which is 1, 1, 1. That's easy. So what's W2? We're going to take X2, which is 1, 1, minus 1, and subtract off, according to the formula, we have to subtract off X2 dot W1 over the length of W1 squared times W1. So, so what is that? That's going to be 1, 1, minus 1. Minus, okay, so what is X2 dot W1? X2 dot W1 is X2 dot X1, and that's 1 times 1 plus 1 times 1 minus, so it's 1 times 1 plus 1 times 1 minus 1 times minus 1. I'm sorry, plus 1 times minus 1. So it's 1 plus 1 minus 1, which is 1. So the dot product is 1. And what is the length of W1 squared? The length of W1 squared is the length of X1 squared, which is 1 plus 1 plus 1, 1 squared plus 1 squared plus 1 squared, which is 3. Okay, so let's go back now and write it down. So W2 is 1, 1 minus 1 minus X2 dot W1, which is 1, over the length of W1 squared, which is 3, times the vector W1, which is 1, 1, 1. And what is that? That looks like, to me, 2/3, and minus 1 minus 1/3 is minus 4/3. Okay, so that's W2. And now we got an orthonormal basis given by W1 and W2. And to get an orthogonal basis, to get an orthonormal basis, we just divide out by the lengths. So the length of W1 we've computed is squared is 3. So we have to divide W1 over the square root of 3. And then the length of W2, what's the length of W2? That's going to be the square root of 2/3 squared plus 2/3 squared plus negative 4/3 squared. And I guess that is, if you do the calculation, I think you get 2 times the square root of 6 over 3. And so we're going to take W2 and divide by its length, which is 2 times the square root of 6 over 3. And if you recalculate, if you write it out, you're going to get W1 over the square root of 3 is 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. And W2 divided by its length is 1 over the square root of 6, 1 over the square root of 6, and then minus 2 over the square root of 6. And that's an orthonormal basis for W. These are unit vectors which are orthogonal to each other. Okay, so that is all I really wish to cover today in this lecture. So we're done. All right.